David Greenberg coming to you from Hamburg. This is the 10th episode of the Machine Learning and Helmholtz-Zentrum Gestalk seminar. We have an interesting set of papers to consider. Mainly we're looking at Raspberry and the background for it. They're using machine learning to do a cloud parameterization for a climate model in a really interesting way. So we'll cover a bit of the background, we'll explain what their goals are, and we'll explain how they do it. Before we get started, I want to make one or two little announcements. First of all, Moritz, Matthias, and I are organizing a session at the UMaRS conference in Kiel this September. I'll put details in the next announcement email, but if you know anyone who's working on machine learning applied to oceanography or marine science, we'd be really interested in having them join our session. And then one more word before we start, just on the general kind of flow and philosophy of the seminar. I think we've covered a lot of really interesting topics. We've had some good discussions, and we've had some sessions where it's been more kind of a little talking into the void and just sort of presenting material. So I'd hoped from the beginning to make this as much as possible like a journal club, where you have anywhere between 10, 20 people sitting around discussing a paper, arguing about it. People have different opinions, different questions. You have people who are novices to the field, people who are experts in one or the other aspect. That in this case, it could be the earth science aspect, the numerical modeling, the machine learning, because they're all different areas of expertise, and kind of seeing people's perspectives and learning from each other. So I think it's difficult, of course, very difficult to get this in an online format. But I think the absolute best way to approach this is just if people interrupt as much as possible, if they ask questions, if they ask questions from previous topics, the things that weren't clear, the things that were interesting, things they want to comment on. So that's always welcome. So that's that. We are gonna jump right into the material. And I think we're gonna start off, Marcel, you're going to present the background on from Schneider et al. But before we do that, I see we have a special surprise guest. Stefan, welcome.
Hello.
Thanks a lot for joining. We're lucky to have the first author of our main paper joining us this week. So Stefan, we can just go through this whole our plan as planned, go through the background, go through the SPCAM paper, explain the MaddenJulian Oscillation. But if your time is limited, we can also jump right into your paper. What do you think?
Oh, I'm good. I'll be here for the entire time.
Fantastic. Great to hear. All right. So Marcel, you want to jump into Schneider et al.?
Sure. If you can release the screen, then I can grab it. Just need to find out how.
I'd ask everyone, you can turn your video off and you can mute when you're not speaking.
Okay. Okay. So as David announced in his email, one of the papers we will be talking about today, and the one we will be starting now with, is Schneider et al. Early 2017 paper. It's a commentary giving us a bit of background about the relevance of resolving clouds in climate models. The big hook that is used in this commentary is the 2015 Paris Agreement with the 2-degree goal, limiting average increase in average global temperature to 2 degrees, and there being a certain budget of CO2 that may be released, and there being a big uncertainty of how much CO2 may actually be released, not to rip this 2-degree goal. As is explained in this paper, the uncertainty comes from the so-called equilibrium climate sensitivity that is a property of different models. So if we have if we look at figure 1, the leftmost panel, if we have a very high equilibrium climate sensitivity, so this is 1 over, so highest to the left of the side, then we have comparatively little allowable CO2 concentration that is still within the 2-degree goal, and if we have a fairly small sensitivity, then correspondingly we have a little more allowable CO2. And how does this relate to the topic of today, modeling of clouds? Is that this is directly here on the second panel, that reflectance changes from clouds in different models, which can be both under future climate situations that are modeled in these different climate models, can be both positive and it can be negative. So each dot here, already in panel A, which I glanced over, but each dot here is a different climate model. And depending on the model that is used, these can actually predict that cloud reflectances from low clouds in the lower atmosphere can either have a dampening effect onto global climate change or a feedback effect. The models don't agree here, and depending on which effect actually is going to come out, we will have the models predict different sensitivities. And in conclusion, how clouds actually turn out to be acting and behaving is directly relevant for how much CO2 is still allowable. Yeah. So the main problem here to figuring out how clouds are going to affect this is tied to the resolution of climate models. So typically at the time that this paper came out, and there's not been that much change within these 3.5 years, is that they had horizontal resolutions of 50 to 100 kilometers. But what is actually really necessary to resolve the relevant dynamics of clouds is more on the 10 to 100 meter range. And the authors make an argument that in order to get there, you would need an increase of resolution of 100 million-fold, and then you would probably need an increase of computational power that's even 1,000 times larger than that. There was an argument regarding the often cited exponential growth of computational power, which we see in figure 2. So we have across different years. And then on the right axis, in the blue dots, you see that on this logarithmic scale, you have kind of a linear development of computational power. So on this logarithmic scale, so in absolute terms, you have an exponential increase that's fairly stable. But as the authors also pointed out, that just increasing the computational power by itself is not necessarily guaranteed that future climate models will also increase their resolution at the same speed. So for purely atmospheric models, these are the big orange dots, you can see that it might actually be true that computational power goes hand in hand with resolution. But another thing that has happened during the past decades is that the climate models themselves got more complex and were added additional and coupled to additional other modules, such as ocean models or complete earth science models that have a bunch of other components, which then eats up a lot of the computational power. So just waiting for computational performance to exponentially increase might not be the way to resolve this issue of resolution in a time pressing manner as we have it. So what the authors argue is to go down another road, as they call it here, these LES, these large eddy simulations, which are limited area models, which operate on a spatial resolution that actually allows to study and represent the dynamics of clouds, but that are not run themselves globally at a high resolution model, such as a general circulation model. One thing that's interesting just to point out, and which we might come across later in the papers, is that even these models might still have unresolvable processes, so one doesn't necessarily completely do away with all kinds of parameterizations, as we've talked about in, I think, the previous session. But the idea is that one gets rid of a lot of parameterizations that have to deal with cloud resolution themselves. The authors point out there's two different ways to combine these local cloud resolving models with global models. One of them is to embed these in every single location of the global model in each grid column. And this is what we will be mostly talking about today when we talk about the superparameterized CN model. They also mention that it could be possible to have these high resolution models only in a few select columns if they turn out to be really, really expensive. And then just one more hook that the authors here already gave, which will be relevant when we talk about the main paper of today, is that when we study these models and we combine these models, there's an element of hindcast. So we can use data that we have in order to optimize how these individual parts play together. And when we have data, we can also try to replace and optimize this in a data-driven fashion. Yes, so this would be it about this paper. If anybody has any questions regarding it, we can talk about this now, or maybe we can also...
There was one question from the chat, I think, which is that is a limited area model just the same as a regional model?
I don't know what kind of regional model you have in your mind. So in this case, it's there's a difference for these models in terms of the spatial extent that they're covering. So what you could have is for instance, a global model at a certain resolution, say T42, which has around the equator grid cells that are on the order of a few hundred kilometers. And then within each of these grid cells, you could have a cloud resolving model, as we will later see in the other papers, which only covers, say, 32 by 32 kilometers. So these cloud resolving models need not even cover the whole local region within a grid cell, and they typically wouldn't cover a local region that covers several grid cells. Is this maybe going into the direction of your question?
I think that answers it more or less, yeah.
Okay. If there are no other questions, then I can hand over to David and he can explain a bit more detail.
Yeah,
these
thanks, Marcel. That was really great. I think this kind of sets up the importance of the problem and gives a vague flavor of what we're trying to do. I'm going to jump into the SPCAM paper, Superparameterization CAM. So let's see. This is, I mean, the concept is I think really important, and it hasn't. I don't think it's become the norm in general circulation models. Still, this is 2005. when this was paper, and actually the work even started a little bit earlier than that. So the overall goal is, as Marcel was saying, we want to capture the phenomenology of what these clouds are doing, especially their effect on radiation, but also other things like precipitation. And as we'll get to it later, some things to do with wind as well. So you can do this by using a model which is got a fine enough grid to resolve these small features of clouds, which can get very small indeed, but it's not computationally practical for a large simulation over the whole Earth or for a long simulation over a whole century. So the idea instead is to somehow capture the effect of these very high resolution features through local simulations and allow the coarse simulation over the whole Earth and these fine local simulations to guide each other. Before I move on, there's another question from the chat. Embedding large eddy simulations without costing computational time, how could that work? Calculations is more, the more calculations you do, the more of a computational cost you pay. That's absolutely right. I think the idea here that we'll get to, I think Marcel hinted at it a little bit, but it's easier for one thing to do these cloud resolving model simulations, a lot of them, a lot of small ones, and to do one big one. They can be done independently. It makes it easier to run on the hardware, but even beyond this, if the grid cell for the coarse global simulation is hundreds of kilometers, you can get away with a much smaller and simpler fine scale cloud resolving model simulation. So you don't have to simulate the entire area. You just have to kind of feed it the local trends and variables, the temperature, the total amount of moisture, and so on. You do a simulation, and then you get results like precipitation, amount of radiation being reflected in different wavelength bands back into space, and then you feed that back into the coarse, large-scale general circulation model. And so this is what these guys try to do. It's a very nicely written paper. They go over a little bit of the history of these approaches. They start with the idea of single column modeling, where you have observational data that says what are these mean trends, the wind speed, the moisture, the pressure, and so on. And then they say, how should I try to predict in a single location things like precipitation, deep convection, other phenomena that I want to parameterize? Is I want to represent abstractly without resolving explicitly on the fine scale. How can I so how can I tune my parameterizations to give the right phenomena, right? So when it's this hot and this windy, it rains this much, and so on. So this was the single column modeling. They never resolved individual clouds, but they looked at the coarse meteorological trends and used this to design their parameterizations. So then going a bit further, they started saying, well, okay, I can sort of build up a library of these different scenarios. I can do some actual explicit cloud resolving models. I can verify that I'm able to recover the right effects on these large scale variables, in particular heating or lack of heating due to reflection of radiation. And then ultimately you can take these small simulations, these small local simulations, and embed them into the grid column, that is a set of vertically stacked voxels or simulation points along the z-axis at one latitude-longitude coordinate pair, and say, at each one of these locations, I'm going to do a little cloud resolving model. I'm going to provide inputs to that cloud resolving model from my large-scale general circulation model, and then I'm going to feed back the results. For example, the overall rate of radiation is reflected back to the atmosphere, or the overall rate of precipitation, or even things like the momentum due to convection. We'll get into that maybe a little bit later. Feed that back into the coarse coarse scale variables over maybe 100 kilometers or so by averaging across this high resolution cloud resolving model in each cell. So this is what they're trying to do. They're building these models, these physical models of clouds to figure out what should be the effect on these coarser models. And it's a nice contrast with the previous paper we covered, which was Schmidt et al., where they wanted to look at, again, meteorological variables, and then they wanted to come up with images of cloud reflection using GANs. But the purpose here was very different. They mentioned this could be used for parameterizations, but they really just wanted to guess what the clouds were. What we're doing here in the superparameterization approach is we don't really care about getting the clouds themselves correct per se. We want to know what is the effect they're going to have on the overall coarse scale model over the entire Earth that we may run for a long time. Okay, so this is how these ideas were sort of developed. They talk about how they were first applied in the simplified aquaplanets with just prescribed sea surface temperatures, no mountains. And they talk about also one of the limits of these small systems, right? When you're doing very small cloud resolving models in each grid cell of your large model, well, you want them small because they're expensive, because they're high resolution. But if you make them too small, then of course there's certain features like certain types of storm systems which you won't be able to represent. But still, they say we're able to get a lot of important phenomena out related to clouds and precipitation and related radiation. So then they'd say, finally, now we're going to not only apply this in an aquaplanet, but we're going to do the full community atmosphere model version with a real Earth topography, a land surface model, so how is water and other quantities interacting between the atmosphere and the surface of the Earth. Proper radiative transfer, so radiation coming down from the atmosphere, from space, being reflected by clouds or not reflected by clouds. And so they're going to try to capture all this stuff using the superparameterization, that is using these small cloud resolving models embedded in their general circulation model. And they're going to try to capture it and see if it reproduces the phenomena they want to reproduce. And this is something I think they're going to come back to a few times in this session. When you design these techniques, you want to design parameterizations or approximate them with neural networks. It's always good to test them on something that you didn't build into your procedures. And one of the common tests here is this MaddenJulian Oscillation, which is a 30 to 60 day cycle of precipitation and rain, especially around Southeast Asia, and the equator. So it was described in 1971 by MaddenJulian. You can see in there, just looking at time series at a location, you can see every 30 to 60 days, you're seeing changes in the direction of the wind. You're seeing changes in pressure. And looking at kind of the more updated version of this on Wikipedia, you see that you have a phase of the oscillation where you have a formation of storms, upward motion, winds flowing inward at the surface, outward at the in the stratosphere, and then the opposite in the other phase of the oscillation. Maybe someone who knows this stuff better than me can explain. I have a question on this, which is the thing, unlike say the ENSO, which we covered, which is a static recurring phenomenon, this thing, it moves east all the time. And I'm wondering, why does it move east? Especially when the prevailing winds around the equator are mainly moving east to west, if I'm not mistaken. So I'm wondering if there's an explanation for that in simple terms, if anyone wants to chime in and answer that. Otherwise, so this is a feature of the observed atmosphere, and it's a feature of up to this point was really not captured in any of these climate models at all. And as I go on to show, the key ingredient that was missing was really the cloud resolving models and precipitation. You can't really get this with the previous parameterizations where people tried to approximate things without resolving clouds. Another key thing that you have to think about when you use this approach is, you have this coarse scale simulation with grid cells 100 kilometers or so, and you have, or 200 kilometers, and you have your meteorological variables there. And then if you have some phenomenon, for example, like radiation or the interaction between the atmosphere and the surface of, you have to choose, am I going to include that phenomenon in my cloud resolving model, as they did in this case for radiation, and it'll be more accurate, or you can resort to just looking at the coarse meteorological variables, and this is what they did for the land surface interaction. So this is a key decision. You basically have to reconsider all your other phenomena and their parameterizations, and maybe re-implement them to use the higher resolution information in the cloud resolving model. So we have the same T42, 2.8 by 2.8 degree grids. For the coarse simulations, we're doing time steps about half an hour. And then I didn't see it in this paper, but I think for the cloud resolving model, you'd be looking at less than, yes, time step of 20 seconds for the cloud resolving model. And they looked at two versions of this. So the coarse scale had 8,000 or so columns, and in each one of them, they're going to put either a 2D version with 64 small cloud resolving columns, or an 8x8 grid of them. And these are going to be 4 kilometers wide as opposed to our 1 or 200. So this is not enough to resolve all cloud phenomena, but it is enough to resolve many important ones. And so you run these. So how you couple the cloud resolving model to the coarse general circulation model? So they do this kind of forcing, which is to say they look at the current state of the large scale variables. This is averaged over the coarse grid, right? 2.8 by 2.8 degrees. And they say, we're going to move our cloud resolving models variables in the direction, slowly, in the direction of the coarse variables, such that if nothing happened, if none of the physics in the cloud resolving model did anything, then after one time step, we would be back. We would decay all the way back into what the coarse model is doing. So any perturbation would sort of disappear after a time step. So we're kind of forcing it or nudging it back to the coarse variables. But of course, that's not the only thing that happens, because there's also all this physics happening in the cloud resolving model. And then at the end of each time step where we've done, so a half an hour, so this is actually, some 90 steps of the cloud resolving model for each 90 or 180 for each step of the coarse global model. Then at the end of that, we're going to take the difference of the cloud resolving model's mean variables and feed them back into things like the overall moisture, temperature, and a number of other important meteorological variables. So they drive each other. The cloud resolving model gets nudged to the coarse meteorological variables, and at the end of the integration, it nudges the coarse meteorological variables toward itself. A key difference here from almost any other parameterization you might think of, where you're trying to estimate tendencies based on, say, radiation, based heating, or precipitation based on meteorological variables, is that the superparameterization has a memory. At the end of each of these half an hour time steps, we don't throw away that cloud resolving model. We use it as the initialization for the cloud resolving model for the same grid cell in the next time step, which means there's extra information stored over the entire run of this SPCAM model, which would not have been present without this parameterization. This is very interesting. And in some ways, it makes what was done in this main paper we'll cover, in the PNAS paper, more difficult and more impressive, that the SPCAM has a memory. Okay, so I want to move through the rest of this stuff pretty quickly so we get to the machine learning part. But okay, we have this memory. So what do? How do they show this is working? first thing they did is they just took forcing data from observations, and they showed that they're able to get reasonable responses from these different resolution cloud resolving models. I think in some cases they are comparing it to, they're using simulations to drive it. But you're saying we can get precipitation, we get precipitable water, we get top of atmosphere upwelling IR. We get a lot of different variables, and we show that we're able to recover them kind of more or less the same regardless of the resolution, and then we get sort of reasonable results. So then they just begin looking at the results of using this cloud resolving model parameterization inside the community atmosphere model, comparing it to the original community atmosphere model with previous parameterizations, which just weren't able to resolve clouds, and comparing to observational data, right? So here's the original version here. We see this very typical, so we're looking at precipitation rate. And here's the superparameterization cam with the cloud resolving model in each voxel, in each column, in each grid cell. And here's observational data. And one thing you notice is this very classical error that a lot of these early, and I think still some climate models make, is this double intertropical convergence zone, where you have these two bands of precipitation near the equator, whereas in reality, you should only have one. And when they use a cloud resolving model to figure out what the trend of these coarse meteorological variables should be in each grid cell, they're able to get something much closer to the actual observations, both in the winter months and the summer months. Of course, it's not perfect. There are some major differences. They're overestimating the precipitation in the Indian and Southeast Asian monsoons. There's a few other, issues like this. But it's overall a big improvement to what they had before. One other thing that you can notice here, compared to, so we talked about I think last time we're talking about climate model tuning, I can find this, the idea of flux correction, and until HZG-M3, you had to correct the radiation balance. This is still a bit before that. So, if I can find well, I'm not finding it in here, but they had to do about 2 watts of flux correction, because this is still, I believe, 2003. And this is 2005, but they still had to flux correct their model at this point. Unlike, I think, a lot of climate models that we would run today. Okay, so I'll just quickly breeze through figures 3 to 10. You can look at it at your own leisure if you like, if you're interested. But basically, what we're seeing here is a whole lot of these meteorological fields. We have absorbed shortwave radiation in winter and summer. And we compare the previous parameterizations to the cloud resolving model embedded in each column, and we're seeing improvements in the matched observational data. Here's the energy flux, 2 watts per square meter. We see long wave cloud forcing, we see short wave cloud forcing, we see all these fields, we're seeing improvements, and none of them are perfect in terms of none of them are capturing the observational data completely, but we're seeing big improvements in almost every case from the previous parameterizations. You look at a few other things. Can they capture the day-night variability? They have this pretty neat graph where they look at the time of day of maximum precipitation. And you can see in the real data, you have these continuous regions where you get more rain at night or during the day. And you kind of begin to capture this with the superparameterization cam with its cloud resolving models, but you do not capture it with the original parameterizations. One thing to note in figure 7 here that I found interesting then is we're looking here at long wave cloud forcing. So this question of the effect of clouds on radiation is is really big. These are big values, right? Like, so, 5 watts per square meter is already big for a climate model. And we're seeing, these are not small differences. And again, it's in the tropics. Just like if you dig into the Schneider review Marcel covered in the beginning, you'll find that tropical clouds have a big effect on radiation balance. And you can see this here. And this is part of the motivation for doing this. Okay. Figure 13 is covering diurnal variations. We just covered that. And figure 14 covers this MaddenJulian oscillation. You can see if you look at kind of the wave number, because here this horizontal line shows a 30-day cycle, and you can see that in the observational data you have this big bump here showing the MaddenJulian oscillation. And you recover this much better in the cloud resolving model embedded into the SPCAM than you do in the standard community access model. And the Madden-Julian oscillation also shows up in outgoing lung wave radiation because the clouds have such an effect on that as well. And this is cool. Like they basically went to first principles. Of course, they have parameterizations of their own. They're not going all the way down and resolving like little particles of snow and water droplets, but they go much closer to first principles, and they're able to actually get a better match to data. And this is really, really satisfying for me. So that is the SPCAM. This is a great time to take more questions. Before we jump on to the next material, we're going to very briefly cover Pritchard 2014 before getting on to the PNAS paper. So anyone has questions on, unfortunately, YouTube is on a 2-minute delay. So if anyone on questions and YouTube had questions 2 minutes ago. If anybody on Zoom has a question now, if you want to ask, if you want to type, or just jump in any time as we move on. So there's a question on the Zoom chat. The answer to my question: the origin of the eastward propagation and other properties of the Madden-Julian oscillation is elusive. Okay, so it wasn't just me, even in 2016. And so thanks, Eduardo. This is a link to a paper which I'm just going to open up. I will put it in the description on YouTube later, but a trio interaction theory. So this is like still a big theoretical question of why this happens. And it's really interesting kind of conceptually, philosophically, in that we now have models computational models which can reproduce it pretty well, although I don't know if in all the particulars, and yet we still can't say for certain how it happens. I guess the models are so complex they don't necessarily lend themselves to a simple explanation. So before we get on to Stefan's PNAS paper, we'll just very briefly cover another paper by Pritchard, who's also a middle author on that PNAS paper, which just says, okay, the point of this is not to resolve clouds for the sake of resolving clouds. The point of this is to resolve clouds to get the right tendencies for all my temperature and radiation and precipitation and moisture and momentum for the coarser-scale variables, which reminds me of a point that I just meant to cover and skipped over in the SPCAM paper. This double ITCZ problem, intertropical convergence zone. They say that remember going back to the beginning, they had these two versions, right? A 2D model of CRM, a 1D model CRM, which had, or rather 2D in height and one horizontal dimension, 64 columns, or a 2x2, an 8x8 3D version. And they say to get rid of the ITCZ, the double ITCZ, they have to include momentum transport due to convection in the cloud resolving model. And that gets rid of the ITCZ. But the simpler version of their SPCAM did not do that, which is a little perplexing in terms of later results. So we'll probably come back to this point. Okay. Pritchard, 2014. They basically just ask, how simple can we make the CRMs? Can we make them very, very small and still get the correct effect on the global circulation models, because this would allow us to be much more computationally efficient. Indeed, the computational cost of embedding these CRMs is not insignificant. I believe, what was it, 20 times slower or something than running the standard.
I think it says at the, if I may quickly interrupt, I think
Yeah,
it says
please.
at the top of the discussion that it's 200 times than
200 times slower than a standard
CM, yes.
CAM. Yeah, okay. Yeah, so this is a big cost to bear. So then Pritchard is asking, can we reduce this cost? And they just say, how much can we simplify the things before we start getting wrong answers? I'll skip over this. If you guys want to look, it's all there. But they look at things like, precipitation, the frequency spectrum of wind, and are we getting the right answers as we make the embedded CRM simpler and simpler? They say basically yes. You can simplify it really quite a ton. They have a nice conceptual point that at some point the limiting factor seems to be, you have this lovely diagram here, if I can find it. At some point the limiting factor seems to be the fact that as convection happens and you've got warm, moist air rising, you got to have cooler air subsiding or dropping down to kind of make room for it. But if your CRM is too small, there's very little space for it to do that, which kind of limits how quickly things can happen and begins to introduce some biases in your results. There's another question from the Zoom chat from Linda. Global models are known to be weaker in resolving anything around the equator. Would that be due to the clouds, or is weaker cloud resolving just one of the results or causes of this weakness? I don't know the answer to that question. I mean, empirically, the including these cloud resolving models in SPCAM does improve the ITCZ. It does improve the distributions of precipitation, the diurnal cycle of precipitation, a lot of seasonal stuff. But is there a more general point about the equator being difficult? I don't know. Maybe someone can chime in either now or at any point. What is there just like a fundamental limitation there? It's a good question. Okay, so Pritchard et al. 2014 show, skipping over most of the details to save time, basically how much you can simplify. So then making this embedded CRM cloud resolving model as simple as possible, but no simpler. We then come to this fantastic paper, which I think was one of the first papers I read when I started to get into earth science, and it got me really interested in these problems. So thanks, Stefan. And we're basically asking, how can we use a neural network to gain the benefits of embedding these CRMs without having to pay all these high computational costs? So I don't know. Stefan, if you want to just present the paper, that's certainly fine. I can go ahead and you can chime in and ask questions. How do you want to do this?
Yeah, I can try to present it. Let me actually get it up so I can maybe share my screen. That'd be easier.
Perfect.
Let me see. Where is it? Yeah, so I would like to mention while I look for the paper that there were a bunch of people that were thinking about doing the sort of similar thing at the same time, and so it was quite interesting because a lot of these groups worked independently from another, and we seem to have the same idea. So let me open the file and then let me share my screen. Okay. There you go. Okay, so you should be seeing the paper.
Yeah.
Cool. Yeah. So thanks a lot. And thanks for the great introduction to what SPCAM is. That takes a lot of the difficulties away from explaining what we're doing here. And so essentially, the gist of it is that what we're doing here is we are trying to replace the cloud resolving model in SPCAM with a neural network. And the reason why this is quite nice is because it's a very well-defined problem. So if you want to build a parameterization with a machine learning model, you need to get a training data set. And oftentimes that can be quite hard to define what exactly you're trying to learn. But in the case of SPCAM, we know exactly what goes into SPCAM. We know exactly what goes out of SPCAM, not SPCAM, of the CRM. We can know exactly what goes in, what goes out of the CRM. And so if we just run a long global simulation and save all the inputs to the CRM and all the outputs to the CRM, then we can use this as a training data set for neural network quite easily. And it should be very easy to plug it back in. And so this is what we did. And I mean, the main motivation again for this is that while SPCAM is good in certain regards, and I would like to highlight that it's not good at everything. So it's good at some things where deep convection is very important. For example, at the equator, you have deep convection. The MaddenJulian oscillation is very much driven by deep convection. The ML HZG, that's all stuff that traditional GCMs have trouble resolving just because of the coarser-scale, which we then can do better with SPCAM. There are some things that SPCAM doesn't do as well. And I think that should be highlighted as well. And that's probably the main reason why, well, it's one of the reasons why it's not used operationally for climate forecasting. The other big reason being that it's still much more expensive than a traditional GCM. So, and this is sort of what we're trying to tackle in this paper is that, okay, can we now make the CRM computations, can we replace them with a neural network? And then it's much faster too. Okay, and so we basically start the paper by going over the Schneider et al. Paper that we covered in the session in the beginning. So same sort of motivation, and right, and so then we go. Let's get to a setup. So what we do is we run SPCAM in an Aquaplanet setup. So this goes back to the old days of running SPCAM. So Aquaplanet, no continents. Makes the whole thing a lot easier because it removes a lot of variables like, different topography and so forth. Everything's kind of nice and the same across the globe. And so we thought that would be a great start for a machine learning parameterization. And so we run our SPCAM in the sort of resolutions that are common. So 2 degrees and 30 minutes. And then we use the 8-column version. So in the previous paper that Mike Pritchard wrote, we compared the different versions of SPCAM with different amounts of horizontal columns. And usually people run it at 32 columns, but again, for just simplicity and to speed up things, we ran SPCAM with 8 columns. Right, and so we ran 2 years of our simulation, of our SPCAM simulation, and wrote and saved all the variables that go into the CRM and go out of the CRM, and train a machine learning model. And so let's go a little bit into more depth about what exactly are the variables that we're looking at here. So as input, you have temperature, humidity, and only one wind direction because we're dealing with a 2D slice here. The CRM is a 2D slice, so there's only wind in one direction. And these are from the global column, essentially. Then we have surface pressure. This is the incoming solar radiation at the top. These are the latent and sensible heat fluxes from the bottom. So we basically need to know exactly what comes in at the top, what goes out at the bottom. And so these are our inputs. Now I would like to mention that this is not the full input to the CRM because the CRM also deals with liquid and cloud water variables. And we decided as a first test to omit those from the CRM. So in our version now, there is no liquid or cloud water. And you might first think, wait, how is that possible? But we'll get to that in a little bit later. And to get the global circulation right, which was our primary goal, that is not paramount. So what's important there is to get the temperature and the water vapor right. And so what we're predicting then is this vector of the temperature tendency, of the moisture tendency. These are radiative tendencies at the top and the bottom, radiative fluxes at the top and the bottom of the atmosphere, and precipitation. And so we basically stack this vector together, and we have an input vector of length 94 and output vector of length 65. And so then we just train a neural network. And the neural network is a really simple neural network. It's just a 9-layer, fully connected network, 256 nodes that amounts to around 500,000 parameters. The great thing is, because we can create our training data, we don't have no limitations as to how much training data we can create. So overfitting wasn't really a problem at all. And so we just trained a pretty big network. And there's really nothing more to the machine learning component here. It was pretty easy to do this stuff from a machine learning perspective. Now you trained a neural network, and so now you need to get that neural network back into your climate model. And turns out technically that's not so easy, because the climate model is of course written in Fortran, and I'm doing my neural network training in Python, of course. So I had to hard code the neural network in Fortran, which I cannot recommend. And I think there are better ways of doing this by now. Like, there were some nice packages that came out in the meantime, but yeah, I had to still hard code it. And well, then you have your neural network in CAM, and I hope you can still hear me. It's just told me my internet connection was unstable, but just let me know.
You're good.
Okay, I'm good. Good, great. So okay, and so now we have this plugged in, and then that version of CAM we call NNCAM. So that's basically the same model version, but instead of the CRM, now you have the neural network. Now we have a third version in the paper, which is we call control CAM, and that's a neural network trained with that's CAM run with a traditional convection parameterization instead of CRM. So that's more akin to what you would do in normal climate models. I have to say though that we are using a pretty old version here of CAM, and so this is not state-of-the-art climate modeling. You can see the results are going to be pretty bad. So don't take this comparison too seriously. So then we look at some results, and the first thing we want to look at is the mean climate, right? That's the first thing we want to look at. And so that's what's shown in these plots. And so what you can see here is because we're on a zonally symmetric aquaplanet, we can average out longitude, which is great because we can plot things on a 2D plot. And so this is height against latitude. And here, what's shown here is the mean temperature tendency. So that's what the neural network predicts. And you can see the comparison here between SPCAM. So that's our ground truth. We can never get better than that with a neural network. Neural network can only be as good as SPCAM. And then this is what the neural network predicts. And you can see this is pretty close. So you have this big heating spike here at the equator. You have some heating here in the extratropics. And you can see that control CAM has this really crazy double ITCZ bias, which is so pronounced that, climate models still struggle with the ITCZ, but not that much. Now, what's more interesting is how this translates into sort of the temperature structure, because this is what the neural network predicts, but then the predictions of the neural network to interact with the rest of the climate model. And so what we're looking at here is the mean temperature structure. And so this is what it looks like for SPCAM, and this is the difference for the neural network. And we can see that the mean temperatures within the troposphere, this is the tropopause here, plotted in the dashed lines. Within the troposphere, we have differences of below 1 Kelvin, which is quite nice. The stratosphere, not so good. And I won't get into too much detail why this is. One reason is, the stratosphere is hard to predict. What we also notice is that if we change the SPCAM setup just a little bit, the stratosphere changes a lot. So it seems to be very sensitive to small changes. Yeah, the model is pretty bad in the stratosphere anyway, so I wouldn't overemphasize this. again, here you can see the differences are quite large. Here we're comparing top of atmosphere solar and thermal radiation, looks close and kind of interesting. Precipitation, you can see the spike here at the equator, and it also seems to do quite well in precipitation. The next thing, so we have the mean structure seems to be quite well resolved. The next thing we wanted to look at was variability. And so, one thing we want to look at is extreme precipitation. And so this is a histogram of precipitation. And ignore the dashed lines for now. Look at the blue and red curves. This is SPCAM and the neural network. And you can see that the extreme precipitation seems to be relatively well resolved compared to sort of a traditional parameterization. So that's quite nice to see. But then if we look at actually the variability of, so up here we looked at the mean of the temperature tendency that comes out of the parameterization. And here we now look at the variability of what comes out of parameterization. And here we can see some deficits. Here you can see, for example, that in the boundary layer, the lowest layer of the atmosphere, there isn't nearly enough variability in the neural network. And this kind of makes sense because if you look at, and maybe I'll bring up the paper that was sort of preceding our paper, and yeah, let's look at this figure. So this is a snapshot from what SPCAM predicts in, this is temperature, and you can see that the boundary layer, so this is a slice, this is one longitude slice, one snapshot, height against latitude of the output of the heating rate from the cloud resolving model. And you can see that here's a tall thunderstorm, a convection tower, and then you can look in the boundary layer and see a lot of noise. And of course, we're dealing here with a chaotic system with a lot of turbulence, particularly in the boundary layer, which is by definition unpredictable. So what the neural network, which is shown here for the same inputs, what the neural network will learn, we're minimizing the L2 loss, right? And in the face of variability, the L2 loss will learn the mean of the distribution. And so you can see that to minimize its loss, it's learned to sort of predict averages and with a lot less variability. And this is particularly extreme here for the moistening rate. And this is also then what we see here. Here, right? So we just don't have enough variability, which comes from the fact that we're minimizing an MSE, where the training data has a lot of sort of chaotic behavior.
Stefan,
okay, so then let's.
Question from from the Zoom chat.
Oh, sorry. Yeah, let me look at the chat.
The question is, due to the Linda, you want to ask? Yeah.
I can look at that.
Okay. Due to an aquaplanet, this precipitation can only be large-scale precipitation, not convective precipitation, as there is no landmass. Is that correct?
I don't think this is correct. So you can also have convection over ocean, right? So if you think about, so the entire ITZZ, the Intertropical Convergence Zone is, well, we don't have a plot here, of course, but let's maybe, I do have a plot. So if you look at it, so if you think about like what's happening, so the ITZZ is a convergence zone where at the convergence zone, you'll have a lot of moisturizing air that is convecting. So you can also have convection over the oceans. So not only over land, you get convection with a diurnal cycle. So typically you have convection in the late afternoon. In the ocean, actually, you tend to have more convection at night. And that is because the surface temperatures are pretty constant, but but you always lose temperature, thermal radiation out into space. And so actually the middle of the troposphere will cool down at night, and then you have a larger temperature gradient between the surface and the middle of the atmosphere, so you tend to get more convective activity. So you can also have convection over land, over the ocean, and that's very common. I mean, if you if you look at like tropical regions, even if there isn't land, you get a lot of convective activity. Okay. Hope this answers the question. Talking about convection, we can look at one of these nice, what are they actually called? I forgot what they're called. These plots. Anyway, it doesn't matter. It's basically a space-time spectrum of the sort of precipitation. We already have seen that if we have a blob here, that's where the MJO is, and that's completely missing here. But we can see that we are able to reproduce the MJO. It's not perfect, right? There's more variability here in the SPCAM model than in the neural network. And again, like one theory about MJO is that the sort of convective variability is very important. And since we've seen that we do have less variability in neural network, it would also make sense that you have less variability in the MJO. Okay, now, so it seems to do pretty well, but one big question that we're trying to answer with climate modeling is what happens with climate change. And so what we wanted to find out is, well, what happens if we take this model that was trained, and I should mention that the run that we trained it on was on a constant climate, right? There was no climate change present. What if we now increase the temperatures by 4 degrees Kelvin? So these are the sea surface temperatures. But we still use the neural network that we trained on the reference temperature for that simulation. And I skipped this, but maybe we'll come back to it later. It doesn't matter. I think it's actually in the appendix, but I can tell you what happened. It didn't do very well. And the reason why it doesn't do very well is because neural networks are terrible at extrapolating. So here's the summary plot of this. So this is a plot where I basically plotted the error, like I just came up with some sort of global temperature error against the sea surface temperature increase. And you can see these red dots here show how the error basically increases if we use the neural network that was trained on the reference temperature. So what this shows is exactly that you cannot ask a neural network to just work in a different regime, because if the input to the neural network are temperatures that are way higher than is ever seen during training, it's not going to work. And what we did then is we trained a neural network both on the reference temperature and on the +4 Kelvin run. And that neural network then was able to do well in both. And it was also able to interpolate for all the temperatures in between. So basically our summary of this is that neural networks cannot extrapolate, but they can interpolate reasonably well. So what this means in the larger picture is that, well, you need to make sure that if you use such a data-driven approach, your training data covers all of the regimes that you also want to simulate later on, right? So that's very important. Okay, so I skipped over this, so let's cover this now. Another question is, we did not impose, and you probably have talked about several approaches so far where people impose physics on the neural network problem. And we did not do any of that. So we basically just had some inputs, we had some outputs, but we did not impose other physical structure. And so what we check here is essentially, well, how well does it learn to represent these physical conservation laws? Because if you're, so the CRM system is there are some fluxes that go out, there's some fluxes that go in, but otherwise it's a closed system, and so we can actually write down what is the energy loss. And so this is what's shown here is basically the so heat can energy can be converted from heat to moisture, or the other way around. But otherwise, if you take into account the fluxes, the top and the bottom, this should be conserved. And so what's shown here is the heat flux essentially against the temperature flux or change, and that should be approximately a straight line. It's not perfect because, as I mentioned earlier, we're ignoring cloud water, liquid water, and this is what the neural network does. And you can see that there's a little more scatter, but there are no outliers, so it learns from data to sort of represent these physical laws. If you look at it globally, again, there is no we do not impose any global energy conservation. Every neural network only, well, the neural network only ever acts locally for one grid column at a time. And these are globally integrated moisture and temperature for 5-year runs. and you can see that there's some scatter in all of the runs, but it's pretty much constant, so there doesn't seem to be any drift. Okay, so that was basically that paper. So, well, what does it mean now? And I think I'll talk a little bit about that, or maybe let me check if there are any questions at this time. Oh yeah, there is one. Would that failure of extrapolation be a sign of an important predictor that is missing in the input? I don't think so. I mean, you're just not covering enough of the phase space in your training data, right? So where we see these problems cropping up when we turn up the temperatures is at the equator. At the equator, it's suddenly 4 degrees warmer than the neural network has ever encountered during training. And so a neural network by itself, a dumb plain neural network will just not be able to handle that, because it will just extrapolate in an unpredictable way. And so even if you had additional input predictors, if your targets, or if your features during test time fall outside of the phase space that you covered during training, then there's no guarantee at all what the neural network is going to do. And so I think that is the crucial problem. So yeah, so basically that was what we did. There were 2 other papers that did similar things that came out at the same time. And yeah, so I can talk a little bit more about what has happened since, how we try to address some of the problems. And well, I think one thing that I should definitely talk about is one of the big issues that happens when you try to do stuff like this, and that is stability. Because what happens essentially is you train a neural network, you plug it into your model. The neural network is trained to predict tendencies for one time step. Then you plug it into this super complex climate model with all kinds of interactions through time, through space. And to be honest, it's kind of surprising that it works as well as it does. And I can tell you that it doesn't always work as well as it does, because oftentimes what we've observed is that the neural network would crash. And we did not find a good explanation of when it would crash and when it would not crash. It wasn't explicitly written in this paper as much, because back then I did a lot of development work on this, and then at some point it worked and it was pretty robust. So even if I trained the neural network again with the different initial seed, it would still be stable in the final run. But it turned out afterwards that this behavior is kind of unpredictable. And so that's a big problem with these neural network parameterizations, is that they're trained outside of the environment that they will be applied at later on, and the behavior is not necessarily always that predictable. And so that I should mention that that's probably one of the big areas that's still unsolved if you do machine learning parameterization, because other teams also struggle with that. If it's not a instability, a crash of the model, then it might be a climate drift, and so this is something that's really kind of tricky about this. And so I think maybe I'll hand it back to David now, and I can talk more about some related aspects if there's time. But otherwise, let me thank him again for having me here.
Thank you so much, Stefan. That was really fantastic. I'm really glad you did that presentation instead of me. I think that was very clear and illuminating. I have a lot of questions, but let's get 1 or 2 from the chat, as long as you have time at least. So one from Felix Stieler, I hope I'm pronouncing that right. How could one make the neural network to be more confident in predicting extreme values? Would more data work? I can give my take on this. What do you think, Stefan?
Well, yes, you need to have enough data to cover the extremes that you also want to predict. The other big problem is that a lot of extremes come from variability, from sort of chaotic variability. So, and we've seen that sort of in this figure is that the neural network sort of predicts the mean. So I think a more more than just more data, I think you would need to have some sort of technique that stochastically predicts the output, or a technique that produces a distribution, because right now we're predicting the mean of the distribution, so it'll be hard to cover the extremes. That's my take on it.
Right on. Okay. That's interesting. So let me ask a conceptual question. I'm struggling with something a little bit. There's a few more from the chat too. I don't want to hog all the time. I mean, you're comparing your neural network to the SPCAM parameterization, and you're looking at kind of the same meteorological variables, at least some of them as inputs. But the SPCAM also has input from the previous time step. It's initialized with the state of the CRM, whatever it was, and it's storing a lot of information there, right? So how are you able to do so well when you don't have access to this persistent variable?
Okay, yeah. Okay, so I think it's, so yes, it does store some information in CRM, but you have to remember we're running with 8 columns, and with 8 columns, the correlation time in the CRM is very short. So I think one of the reasons why this does not play a big role is because we're training with 8 columns. And then also, I don't think it's totally, even if you run in 32 columns, I don't think it's totally clear yet how much convective memory actually matters. That's an active area of research. Most traditional convection parameterizations.
I mean, I'm just saying, as an avid person, observer of the weather, and as someone who lives in Hamburg and frequently gets rained on, right? If the meteorological variables, the coarse ones, are getting updated every 30 or 60 minutes, I mean, there's definitely a memory in convective weather systems there, right? That lasts for maybe more than an hour.
Yes, there is, and I think there is an argument that it is important. However, you also have to think about that. What a convection parameterization does, and what it should do, is it should provide the right feedback to get the correct large-scale circulation. And I don't think it's absolutely clear how important convective memory is for that. There are definitely arguments that for phenomena like the MJO, this is very important, right? But I don't think it's a solved question, and most traditional convection parameterizations do not have memory, and modern convection parameterizations do relatively well. So I don't think it's as black and white, but for the reason why it didn't matter here is because we used 8 columns, and I think 8 columns, you don't have a lot of memory.
Okay, that's really interesting. Okay, I have more questions. But
maybe you can answer some questions from the
Zoom chat. Yeah. So the first one was, how would this model work?
How would this model work when adding? Yeah.
Go ahead, Steph.
Yeah, sorry. Okay, so I'll take it. So how would this model work when adding orography? Good question. There is a group that, Mike has a person that's working on this now. It makes it a lot more difficult. You're now working with a non-uniform grid, right? The grid, usually in climate models, you have a grid that's terrain following. So now you have to deal with that. And if you have orography, that obviously means you have land, and you want to get the correct coupling to the land. So you need to predict all kinds of variables that couple to the land model. So it makes it a lot more difficult. And I do not think that at this stage we have done an online simulation. So meaning a coupled neural network, CRM, GCM hybrid run for orography. But it makes it a lot more difficult. And but hopefully we'll see some first results of this within a year or so. Let me just go to the next question. So energy conservation is a very nice side effect. Would the covariance between output variables delta t and p also be realistic? Well, I don't actually know. I don't actually think I looked at that explicitly, so I don't know if the correlations are actually observed. So I don't have a good answer to that.
That's a really interesting question. So I'm struggling with one more point. Maybe you can resolve for me. If you look in the original SPCAM paper, they say that in order Khairutdinov et al. they need to include momentum transport by convection to get a single ITCZ. But in your PNAS paper, you didn't do that, but you still got a single ITCZ in your SPCAM. How is that possible?
Yeah, it was also not in the SPCAM version that we used. There was also no momentum transfer.
But then, why did the original paper say you need this?
So I do not know if there has.
I mean, maybe it depends on.
I don't know. I do not know the answer. I could assume that maybe what happened was that, you know, people, maybe SPCAM did get better since the original paper, and they didn't need momentum transport anymore, but I don't have an answer for this. I just know that this SPCAM version also didn't have it, and that also doesn't have a double ITCC, so not sure.
One last question from me. Go ahead. Sorry, Marcel.
May quickly read out that the original version was SPCAM with CAM version 2.02, and you worked with version 3, right?
3, yeah.
I see. Interesting. So my last question here, and maybe you can just get into this briefly if it's complicated, but you mentioned that you have this CRM embedded without condensed water. How does that work?
Well, so yeah, so again, like
Stefan, we're losing you for a second. I'm losing audio. I think you're cutting out a bit there. I can't hear. From your screen share, it looks like you've got some download going in the background. Looks like we lost Stefan. That is unfortunate. Hopefully he will pop back in, or we may never know the answer to that question. All right, well, we'll wait another minute or two before ending. If anybody else has a question or any comments, hopefully we'll get Stefan back in a second. I would just like to say I really found this to be one of our best sessions yet. I really enjoyed this.
Sorry,
Stefan, hey.
It was gone. Yeah, sorry, my internet just dropped out. What was I talking about? Maybe I can finish my point.
The question was, what does it mean to have no condensed water in a CRM?
Yeah, no, so exactly. So condensed water, I mean, in the simple aquaplanet world, I mean, so it only matters for the convection parameterization or the large-scale microphysics, but we're parameterizing all of that. So basically, we're parameterizing with our CRM. I should have added that we're not only replacing. So the CRM is also doing the radiation in SPCAM, right? So the radiation also happen. Well, that doesn't matter. No, that's not actually true. That depends on which version you're using. But with our neural network, we're doing the convection parameterization, we're doing the radiation parameterization, and we're doing the microphysics parameterization all in one. So there are no other parameterizations in the atmosphere, okay? So this means that there technically is no reason for us to have cloud water or ice, that no other model component depends on it. So we're just hoping that the neural network does not need this information to make good predictions about temperature and moisture. And this turned out to be the case. I do think that some of the issues that we've seen with not enough variability at the boundary layer do have to do with the fact that we do not have cloud water as input or output. And so, of course, you want to have that eventually, right? Like, it's just that it's, from a technical point of view, kind of difficult because these are very skewed variables. They're, like cloud water will be 0 mostly, and then there's some clouds somewhere. And so it turns out that that's not that easy. We tried to implement it, but we often ran into problems that we had negative concentrations and so on. So we just dropped that out, and
I see.
it still worked reasonably well. But
when you
wanna have
generated
it
the training data with SPCAM 3, the CRMs did have cloud water in them, right? And they had that persistent. Okay.
Yeah, we just didn't use it then. Yeah, we just didn't, kind of ignored it. Yeah.
Great. If there's no more questions, I guess we can wrap up. This was, I was just saying, a really fantastic session. Thanks, Stefan, a lot for giving us this read through of your paper. It was really great.
Thanks for having me.
All right, and thanks to everyone who joined. We will see you again in another 2 weeks.